All right, hi everyone. My name is Melody and I'm joined by Ethan. Our project is efficient COVID-19 classification in low resolution scenarios. So to start off, we're gonna present to you the motivation and problem statement of our project. Firstly, there's a need for fast and accessible diagnosis of COVID-19 patients. In general, for most medical related classification and detection, this is a big thing, always wanting a fast and accessible way of doing it. The second motivation statement is that accurate and efficient detection methods that do not rely on high resolution imaging can reduce costs and patient discomfort. So for this reason, we thought, okay, let's develop a machine learning model and pipeline that can accurately detect COVID-19 from CT imaging, even in situations of low resolution or compressed formats. So to target and to tackle this idea, we took a look at various COVID data sets and chose the COVID XCT3A data set, which is broken into these three classes. First, normal control scans, CT scans. Second, community-acquired pneumonia scans. And thirdly, COVID-19 specific pneumonia. So these are all CT scans of the lungs. A lot of the misclassification occurs between the community-acquired pneumonia and the COVID-19 pneumonia. So the data set itself is a pretty extensive and pretty large data set consisting of over 400,000 CT slices. It's diverse. These patients, 6,000 patients, come from all over the world, and the images are 512 and 512 in resolution, so pretty high resolution. It's split like so, and we find that compared to its predecessors, COVID XCT3, CT1 and CT2, this data set really brought a great starting point for further development in COVID detection methods in machine learning. So to start off, this is our general approach. We begin with our COVID XCT data set of these images of 512 by 512. We do some first data pre-processing and artificially downsample images to resemble undersampled or compressed images. In this case, we downsampled to 64 by 64. And then using a super resolution network, pre-trained network called FODON, we upscale the CT slices to an appropriate size to then inject into our two-stage binary classification method. So first, I'm going to explain a little bit more about this super resolution model, and then Ethan will talk about our two-stage binary classification. So FODON is a feedback adaptive weighting dense network. The general idea is that this super resolution feedback network is built upon several feedback blocks. These blocks take in low resolution input images and output intermediate feature maps. Those feature maps are then fed back in to generate refined outputs in an iterative manner, with the final end result being a high resolution image. So those feedback blocks are a series of convolutional layers followed by nonlinear activation functions, and each block is built with up and down sampling layers with dense skip connections. Other CNN approaches easily rack up the number of parameters and take up a lot of storage during training. So this process is pretty well known for its ability to reduce the resources needed through the iterative refinement process. So instead of storing multiple high resolution intermediate feature maps, the feedback network store a single low resolution feature map and then iteratively refine it to generate that final high resolution image. So in order to use this process in our architecture, we were able to find 3 pre-trained medical imaging models of this approach. And those models are 2 times resolution, 3 times resolution, and 4 times resolution. So for our initial approach, we're using that 2 times resolution. Here are some initial results we saw with our ground truth CT images from the data set in 512 by 512. And then we performed a 2 times resolution from 256 up to 512 and saw that structurally and visually the CT scans presented pretty well reconstructed with the super resolution techniques. Ethan's
okay, can you hear me?
Yeah.
Okay, great. So following the upscaling from FON DN, we have that 128 by 128 resolution CT slice. This is then sent into a two-stage binary classifier. The first stage separates out the COVID class, and then the second stage binary classifies those last two classes, normal and cap. This is advantageous for this because with high resolution imaging, you have a lot of data you want to process. So if you're trying to separate all three classes out with a single model, it requires a lot more computation. So separating out into two stages like this allows us to reduce that computation and give some more of that extra time we get to the super resolution prior. So let's hop inside these models so that I can explain them in a little bit more depth. So the first stage well, both stages are just pretty simple CNNs. The first stage is based on the DenseNet implementation from TensorFlow, which is then followed by a few fully connected layers and finally a sigmoid activation function to split it up into those two classes. We get that non-COVID class, which is then passed on to the next stage. The second stage instead uses an Inception v3 implementation. And then this is again, very simple CNN followed by a couple of fully connected layers and then a sigmoid activation function to finally classify normal and pneumonia. And so from this, we get our COVID class, our normal class, and our pneumonia class. So yeah, the output of that is our final classification, and then we can compare, the actual predicted class versus the truth labels to get a confusion matrix. So here are some of our preliminary results, and the big, the main takeaway from this is that the 64 by 64 resolution CT scans top out at about 75% accuracy. We were struggling to get anything above that, and that's validation accuracy. Whereas with 128 by 128, we're able to get considerably higher accuracies of around 85%, and we actually have some better runs than this. We just didn't have the chart saved, unfortunately. And then separately, we also were testing the influence of super resolution of the FODON network at lower resolutions because we saw it was successful at 256 to 512, but where you start from lower resolutions, you have even less data to work with. And so what we saw was if we started at 32 by 32, the PSNR scores are just unacceptable. We found that anything under 20 was just unacceptable. And you could actually see that visually how mismatched 128 is from the ground truth. So we bumped it up a little more to 64 by 64. And this did get our PSNRs into like an acceptable range, but still not great performance. And we were kind of limited by the amount of resources we have to train with. So if we started from 256 and went to 512, we'd have much better performance, but to handle those 512 by 512 images is just unrealistic for the resources we have available to us. So our next steps for finishing would be to integrate the super resolution and the binary classifier into a single file. So right now we're just manually taking the images from the super resolution and inputting them into the binary classifier, but we want it to be more automated so that it's easier for other people to run our code and adopt it. Once we have that finished, we're going to run a large validation run with a roughly 5,000 CT slices and then chart the PSNRs and classification accuracies of all those. And using that data, we'll finish up the report and submit. And that's the end of our project.